Everybody said thanks for the invitation, but thanks for the invitation. This is cool. I'm going to talk about radiation. It's a broad subject. There's all kinds of interesting work being done. I should just back up probably and say that I'm a very much domain scientist, and my experience with machine learning is very limited. I hoped so. It's all right? Yeah, all right, very well. There's some really interesting work being done, particularly in remote sensing, which we sort of consider a branch of radiation typically. But what I'm going to talk about here primarily is radiation for forward modeling, so for prediction. Before I do, I want to make two quick advertisements. One of them is something Mike Pritchard and Pierre Gentine have retweeted for me. So there's this interdisciplinary computer science conference that's really meant to, includes the humanities and social sciences. PASC here, and they're seeking mini symposia, and so that's 4 talks, each half an hour long. So that's kind of cool. Please consider submitting to that. The other is that I have been cheerleading some efforts at NVIDIA, and I was told this morning, that they have finally finished this interface to the PyTorch libraries from Python. So Alistair referred to this earlier. It's been one of the things that's made it very, very hard to move machine learning into these legacy codes is the inability to evaluate models conveniently, evaluate machine learning models conveniently from Fortran. This is meant to alleviate that. If you would like to know more, you can ask me and I'll give you the email of the people I'm working with at NVIDIA, because this is not my jam. Yeah, okay. People have been doing what we might consider machine learning for radiation for 20 years. And as far as I know, in the context of predicting processes, so using this in a forward model to represent a particular process, this is the first example. These are the first examples. And they date back to the late 1990s and the early 2000s. And this was people using neural networks to emulate what they consider to be an expensive part of the forward model. So they are the radiation parameterizations, the low order models that go into the weather forecasting or climate projection models. And they did this, so that it was, simple, relatively simple artificial neural networks. The main point of this was to increase computational speed. So you're starting with a thing which is already approximate. You are learning its behavior with a neural network, and you're doing that so that you can make things faster. People are still doing this. And I find that sort of interesting. This, but there's some interesting wrinkles to it. So this is work by Ryan Lagerquist, who's at Colorado State, working with people at NOAA in Boulder. And he's built this fairly sophisticated, a UNet plus architecture to emulate a fast radiative transfer parameterization. It's relatively complicated, it's relatively sophisticated, and it works real well. And these, wow, that's probably going to be hard to see. But these are what are called reliability diagrams. So they are a way that's often used in ensemble probabilistic forecasting. And so they show you the results conditioned on the prediction. So the evaluation is conditioned on the prediction. And, roughly what he's showing you is that this works well across a wide range of circumstances. I'm left a little bit cold by the idea that the main reason for doing this is computational efficiency. And I could rehearse for you, but I won't bother to do it here, why I just don't think this is really being quite ambitious enough for what we might do with radiation. So I want to say that in general, the computational cost of radiation is no longer really a limiting factor in most of our predictions. So this I don't find so very compelling, the idea that you would do this so that you could do it faster. So the idea that you would learn the behavior of a simplified system so you could get to the result faster. It's not really what Ryan Lagerquist is doing though, actually. He's training on what you could call a fast-ish calculation. So it's substantially slower, and I'll come back to this theme. It's substantially slower than you would normally afford. It's slower in two ways. One is it's more accurate in an angular space, and the other is that it's more accurate in the spectral space, by which I mean the electromagnetic spectrum. So it's not a heroic calculation, but it's one you couldn't afford. And so what Ryan has done is to train his neural net on this. And so in this way, this is kind of potentially promising, because now what you have is a proxy for a much more, or a modestly more accurate calculation, and that's kind of neat. The computational cost of producing the proxy data is the limiting factor. So in Ryan's case, this isn't a particular, there's not a real limit here, but for problems I'll show you in a little bit, this potentially really is. One thing I want to point out is that what Ryan has done is to emulate the entire radiation package. And another approach he might have taken would be to say, I'm going to do this calculation using an existing fast model as one that could be run inline, and learn the correction between this and the more accurate, still fast-ish calculation. So I think these are potentially interesting ideas, right? Using the machine learning to buy yourself a little bit of accuracy, buy yourself a little bit more physics. I want to point out, and I think this might be potentially interesting for the machine learning people, but maybe not, why you might want to build a forward model and never use it to predict the future, but to predict the past. And that's because we do a lot of, in the weather forecasting context, our ability to estimate the state, data assimilation that you've heard about, is super important for accurate forecasts. And I think arguably the most advanced ways we have of doing this are what you could think of as trajectory matching. So it's called four-dimensional variational data assimilation, but what it's trying to do is adjust the path of the model through the time history of the observations. And in order to do this in a variational way, you need the derivatives with respect to time. So you need to be able to know the tangent linear behavior of the model forward in time and the adjoint behavior of the model backward in time. We used to build schemes that did this by hand. Poor Adrian Tompkins spent a year building, a cloud scheme that was only intended for data assimilation and never used directly in a forecast. If you model the behavior with a neural network, of course, you get that for free. And so this is starting to be done. Here is a work by Sam Hatfield at Oxford, where they're doing this for non-orographic gravity wave drag. But there's nothing to keep you from any parameterization that you can build a machine learning model for. You can, in certain architectures, you can differentiate and use to build these tangent linear and adjoint models. And if you do it carefully, there is no distinction between the forecasting system running with a hand-built adjoint and one with this neural network. And really the only, these are errors as a function, obviously, of forecast lead and pressure and latitude. There's only averaged. The comparison is between the model with a hand-built adjoint and a model with this neural network adjoint, and hatching indicates areas of statistical significance, and there's no hatching. All right, so this works quite effectively. Keep in mind that they're trying to reproduce behavior for which they have an existing adjoint. But the problem's more general, and this isn't something we know how to do, particularly for radiation. Okay. So when we think about learning, machine learning parameterizations, or really when we think about parameterizations in general, we're often talking about modeling emergent behavior. Tapio talked about it as being coherent structures. And these are things that are, very, very, well, let's just say that they're emergent behavior. For radiation, we have equations that we know as well as the Navier-Stokes equations are known. And so you have this flux. Oh, let's see, you set this up. Yes. You have a flux, which is a hemispheric average. So it is the projection on the normal vector of the intensity, which depends on this direction omega and its position x. It's an integral over all of the directions, so over the hemisphere, both these azimuthal angles and these polar angles. It's that projection on the norm. And we can compute that intensity through this equation, and it's basically the intensity is determined by the boundary conditions and by the distribution of this extinction, this beta, and by the distribution of source terms. So for long wave radiation, the Earth shine, that is determined by the temperature of the atmosphere and the surface. And beta is a property of the medium, the extinction in the medium. So when we make a parameterization, we do three things. One of them is that we assume that the variability is all in the vertical, and that lets us change coordinates to the vertically integrated extinction, the so-called tau. Another is we do some angular integration. So rather than solving for the intensity as a function of angle, we'll simplify the equations by integrating over them angularly. And that gives us, instead of integral differential equations, it gives us sets of coupled ordinary differential equations. And all of these things are all of these equations hold for monochromatic. So for a single wavelength of light, there's a broad spectrum, all the colors of the rainbow, all the colors you can't see. So we have to integrate spectrally in order to account for the energy in each one of those. And this we typically do not with a continuous integral, but by various tricks. But to reduce that to quadrature in some finite number of points, typically tens to hundreds. The reason I want to show you this is just to say that from a theoretical point of view, we're on extremely solid ground when we talk about parameterizing radiation. And there's not, to me, a very compelling argument for replacing this with machine learning. But in order to do the practical calculation, there's a huge amount of empiricism that's involved. So if you looked at the top of the atmosphere, at the spectral, here, all the colors of electromagnetic radiation leaving the top of the atmosphere, you would see something with an enormous amount of spectral structure. And that's because the clear atmosphere in particular, is got millions of absorption features, spectral lines, absorption lines, each one of which corresponds to a different quantum mechanical transition. And when we want to do this integral, we go to catalogs that have these millions of spectral features, and we're going to go and calculate how the absorption of the atmosphere depends on temperature and pressure, because these modify the shape of the spectral features, and then do this radiative transfer calculation. So there's a lot of empiricism in the end result of a radiative transfer calculation. And of course, empiricism is a great place to apply machine learning. So here's an example of something that's just meant as a practical shortcut. I said that what we typically do in order to make the calculations affordable in a radiative transfer parameterization is we reduce that spectral detail to a finite number of spectral points. And then typically you'll have lookup tables. So you'll have something that tells you how the opacity of the atmosphere changes as a function of temperature and pressure in some spectral region. And we have built such a code that's in fairly wide use now. And someone else came along, Menno Veerman here from Wageningen University in the Netherlands, and he said, I can use machine learning to replace your lookup tables with neural networks. He can do that with really quite simple neural networks. So you have 1 layer and 2 layer and, sort of 32 or 64 elements. The simpler networks don't do as good a job in reproducing the lookup tables as do the more complicated networks, but they all do a pretty darn good job. And they are faster, not surprisingly, because you're trading dense linear algebra, which computers are pretty good at, and for which we have highly optimized algorithms, for linear interpolation and a lot of basically very expensive memory access. So here's a place where we've taken empiricism in the form of tables and replaced it with empiricism in the form of neural networks. And it seems to work pretty well. And it buys you, for this piece of the radiation code, factors of 3 or 4. So I said that I thought that learning the entire behavior of a approximation isn't such an interesting use of time. I showed you an example where we might use the machine learning to just accelerate the piece of it that's primarily empirical. I think the most interesting opportunities are in trying to relax a bunch of the approximations that we make in order to make the calculation affordable in online models. The biggest one of those, the source of the most errors, of the non-random errors, comes from, I said, this one-dimensional, this projecting the spatial problem into a single dimension. This is actually 3 different kinds of approximations. The first one, roughly speaking, is shadows the flow of radiation between elements of the mesh by which you discretize space. So one way to think about that would be a shadow which is cast by a cloud or a rock in one part of the domain into the neighboring domains. This doesn't, for most of our models, this doesn't really come up that often. And so I'm going to just sort of ignore it, but this is very much like an advection problem. The second is that you might think of those equations describe the flow of radiation in a uniform medium, and the medium is in fact anything but uniform. So in particular for clouds, for models, even at sort of weather forecasting scales where they're 10 kilometers apart, there's a lot of variability at much smaller scales. And you saw pictures of this that Tapio showed, and you know this just from looking out the window. The scales over which this inhomogeneity matters are not unbounded. There's a scale, a spatial scale at which radiation, you could think of it as a little bit like diffusion, but there's a scale at which radiation smooths over the inhomogeneities. That's related to the opacity of the atmosphere, but let's say it's of order 100 to 1,000 meters. So the scales over which we're worried about inhomogeneity are not unbounded, but there's still a lot of variability at small scales. If you'd like to understand how that distribution or how that variability plays out, you need to know 2 things. One is you need to know the variability, the one-point statistics of opacity in a given layer. And then, because the radiation is non-local, it flows up and down in a column, you need to know how these layers are connected one with another. So there are several approaches operationally. When you think of what is it that you're predicting in a subgrid model of clouds, oftentimes it's not only the mean, but it sometimes might include higher order statistics. As far as I am aware, there are, that is to say that the layer-wise distribution of opacity might be available to you. For sure, the vertical relationships between opacity in one layer and opacity in the others is not known to you. At least, and someone can correct me if I'm wrong, but as far as I know, that's not something that's predicted by any subgrid model. And so I would stress this, although I'm not going to show it. I think there are opportunities to learn empirically these kinds of relationships from data that would lead to potentially, better representations of the empirical behavior we see in the world that would lead to improved predictions of radiation, not because you'd be improving the theory, but because you'd be improving your description of the medium in which the radiation propagates. The third piece of this approximation is the idea that all of the radiation flowing between different elements within your larger domain doesn't pass from one location to the other. And relaxing this assumption is actually pretty hard. So it requires solving the full 3-dimensional radiative transfer equation. It's also conceptually hard because you need to know now not only the one-point statistics, but the spatial arrangement of this data, of opacity in space. And so the degree to which these second 2 pieces affect the domain mean fluxes depends a lot on the spatial structure that you don't know anything about at small scales. So lacking a theory for how that stuff, how the water, the reflective water or the absorbing water is arranged within a grid cell, you're back to empiricism. Here's work. That figure might look familiar. I think Tapio showed you this one. I'm going to report here on work from another student in Tapio's group, actually, Claire Singer, who did a really interesting piece of work to try and assess just how important it was that we were ignoring this so-called three-dimensional radiative transfer effect. And so she started with, I guess, a small subset of simulations from your LES library. And so the thing that I would draw your attention to here is that the morphology of the clouds is different and their aspect ratios are different. This one's very shallow and fairly planar and uniform. Can I go back? And this one is, the aspect ratio is much taller. And it's much more sort of lumpy in space. And she did very expensive radiative transfer calculations at a variety of sun angles. And the reason for doing that is that the physics of the way that the spatial distribution of opacity interacts with light has a lot to do with the direction of the solar beam. One way to think about it would be, you know, if it's straight up and down and the shadows are being cast below, the light comes in the side and escapes out. If the sun goes to the side, then you're illuminating the sides of the clouds and so on. She explains this well. And so she has, for these different cloud morphologies in the different colors as a function of the solar zenith angle, she's asked herself, what is the bias which is introduced in the radiative flux? You can see that it varies from a few watts per meter squared to very large, that the estimation of the albedo, so that's sort of the normalized amount of light that's reflected, varies by %. She has fit that with a carefully constructed linear model to an observable, so in this case, how much water is in the clouds. And she has used observations of this the distribution of this observable to estimate how much the neglect of this piece of physics impacts fluxes in the, or let's say the tropics and the extratropics, but not the polar latitudes. And that's this map up here in the corner. I would maybe draw your eye to this side of it, which is the zonal mean, and where you can see that the neglect of this physics is of order watts per meter squared. And just to scale, that's the same scale as the radiative forcing that drives climate change. So for a piece of missing physics, this is bad. So I thought that was pretty inspiring. People have been thinking about this for a while, and there's an approximation to three-dimensional radiative transfer that was built by Robin Hogan, who's now at ECMWF. And it looks, you know, it looks like a lot of other parameterizations in the sense that there's a lot of structure that's built into how he treats this. So there are a variety of different cloudy regions, a finite number of them. They are defined by a parameter that determines the variability. And then there's coupling from each region to all of the other possible regions. And there's also terms that account for the exchange between different regions, which corresponds to this three-dimensional radiative transfer. And those are parameterized in terms of a third number, which corresponds to, roughly speaking, the length of the edge between any two regions. So it's meant to treat biases, and it's meant to treat them in a conditional way. So one of the things about something that depends on a solar zenith angle is that the distribution of solar zenith angles, even in the diurnal average, isn't uniform across the globe. And you can see the signature of that in Claire's figure. And so he's trying to treat biases, including biases that depend on the solar zenith angle. Again, Spartacus, which is this parameterization for the three-dimensional effects, is about 4 times or 5 times slower than the existing radiative transfer parameterizations, and so it's not going into an operational prediction anytime soon or a routine prediction anytime soon. But you can learn it. You can, and in particular, you can learn the difference between this and neglecting something which is in all other ways similar but neglects these region-to-region transfers quite well with machine learning. And so this is work that David Meyer did. It's actually interesting. I made this argument that we should be learning the corrections at Oxford. I went to ECMWF the day after Oxford. I said, you should do this. And lo and behold, this paper appeared. It was just delightful. And so what they've done exactly that. They've taken the non-three-dimensional version of Spartacus, which is called Triple Clouds, and they have over 25,000 samples from an atmosphere produced by ECMWF. They have calculated the difference between Spartacus, the version which accounts for three-dimensional flow, and the version which does not. They've been able to learn that quite well with that difference quite well with a neural network, including things that would be very hard to do with benchmark calculations like Monte Carlo. And so that was cool. So this solves, the way this works is that you take the approximations you can solve and you solve them. And you use machine learning to do the residual, to add in the missing physics. And I think that's kind of neat. Again, this relies on a fast-ish model, so something which is 5 times slower than you could normally afford. It's a parameterized model, and so one of the things you could do is you could say, well, could we calibrate such a model? And I'm a little bit abusing your terminology here, Tapio, but this is work done by Najda Villefranc, who's at LMD, who's a postdoc at LMD in Paris. And what she's done is she said, I'm going to take a library of large eddy simulations. I'm going to compute the benchmark answer with a Monte Carlo, and then I'm going to build an emulator for Spartacus, which explores it's a very low dimensional, three-dimensional parameter space. And I'm going to build that. And so I'm going to use that emulator to tune the 3 parameters that go into Spartacus. So there's this highly parameterized version of representation of cloud inhomogeneity. And I'm going to ask what values produce the best answers. And the thing that I would just draw out for you here is that there's a lot of inconsistency depending on the answer you seek. So if you want the atmosphere, the reflection at the top or the bottom of the atmosphere produced by Spartacus to be consistent with your benchmark calculations, then you find that you have these values of the parameters. If you, and so this relates to the lumpiness, this relates to the vertical, and this relates to the edge length. If you want to get the absorption, even just the integrated absorption within the atmosphere, right, you need a very different description of clouds. Here. If you want to get them all right, of course, your scales are intermediate. But the thing that's maybe more troubling to me is that if you go and you inquire of the cloud fields themselves, what the parameters would be, they don't look like the parameters that give you the right fluxes. And so to me, this implies that there's a fair amount of structural error in the model. This is sort of borne out when you go and assess this with out-of-sample data. So one thing you might say is, well, maybe the predictions are not particularly sensitive to the values of the parameters, but that turns out not to be the case. So I have to reconcile this with what I know about the way Spartacus was built, because of course, in the original development, it looks to be pretty good at reproducing these kind of statistics. So I need to understand how that has not happened. But I think what it implies is that there's not really a shortcut that I can see to understanding how these 3D effects are made manifest in the radiation fields. And so that data is likely to, the data you would need to assess that is likely to remain sparse. So it's marvelous if there's a library of 1,000 LES simulations. That would be a source of data that would be very, very rich. I would just point out that even in the presence of that, we still need Monte Carlo simulations, so simulations of the radiative transfer, that will be quite expensive. Getting the boundary fluxes right is one thing. Getting the local heating rates right, even the column averaged heating rates right, is quite a different computational task. I nonetheless think it's probably, it's the way I see moving forward. I would be interested in talking about feature identification for people, with people here, because it's not at all clear to me that we really know what aspects of the clouds determine this. And I think that could help with our sampling strategy. And more to the point, even in a model, you don't, in a discretized model, you don't know what the small scale state is. And so with my 1 minute left, I would like to point out that it might be that you don't, that the route to understanding the 3D fluxes doesn't go through a parameter space explicitly. But maybe the idea would be to learn the problem and its solution at the same time. This isn't a great example, but it's an example of what I'm trying to talk about. So this is a place where someone has used a neural network to replace what are often called radiative kernels. So they're asking, what is the sensitivity of the radiative flux to the local state? This is useful for analyzing, how the changes in the physical state change the energy balance at the top of the atmosphere. So we do this kind of thing for climate feedbacks. And what someone has done, this is from Yi Wang's group at McGill, is that they have done this for monthly averages. And so what they have learned is not the behavior of radiative transfer, but all of the subgrid, some sub-timescale variability, right? How if you have a monthly average, which is what they're working with, if you have a monthly average state, how does that a change in the monthly average state, how does that manifest in a change in the monthly averaged fluxes? And because the radiative transfer is so nonlinear, that's not at all trivial. And really what it means is that they have learned the mapping. So I will stop here so that Alistair doesn't beat me up. I think the opportunities are twofold, right? They're not for speeding things up in radiation. They're rather for representing the empirical knowledge, as I showed you, and they're for providing corrections to approximations. I think the challenge for applying machine learning is going to be that the data for a lot of what we want to do is really, really sparse, and that I'd like to talk to you about. And I have two other neat problems that I want to do. One is dimension reduction and one is equation discovery. So if you want, I'll be here for another week and I'd love to talk to you about it. Thank you.
Thank you very much, Robert. Okay, so you know what I'm going to ask. Any questions from our more important members here? Any questions at all? Oh, okay. Please, Stefan.
Hi, thanks for this really interesting talk. I'm curious how feasible you think it would be to for example, suppose you have basically these like very. Is this working?
Yes, yeah, but he's just too tall.
Okay. I'll hold it a little closer. I'm curious how feasible you think it would be to use, if you wanted to use machine learning to entirely replace one of these radiative transfer schemes, even if I know that even for, say on like one of these like much better training data sets.
I mean, at some level, where is escape? Some level that is this work. So that's the original work, right? The original work by Krasnopolsky and others was to replace very very rough approximations with machine learning. And as we have discussed, but which I would reiterate here, I just think this is not setting our sights high enough.
Right. I guess I mean, like, so I guess I'm wondering.
And so, yeah. So that's this, right? That's this idea. The idea that you would build a more this is a learned model of something substantially, well, there's two ways in which the training data is different, and that is that it has substantially more angular resolution and substantially more spectral resolution. So I think that's not an unreasonable thing to try. I think the real question, though, would be to ask, why would you learn the whole thing rather than the correction to something approximate? Partly that's just you can get yourself into less trouble that way, right? The corrections here will be of 10% of 10 or 20% of the magnitude of the physically based approximate calculation. And I guess the question I would have is, why would you not do that and then add a correction just to keep yourself, on the straight and narrow?
Fair enough. Thanks.
Micah.
Hi, yeah, thank you. I guess I have sort of two questions again that are sort of intermingled. Sort of being around what I think you called feature extraction. So extracting different components that you're interested in.
Yeah.
And I guess first a comment, I see that going hand in hand with dimensionality reduction to some extent, all depending on what you mean when you say dimension, perhaps. And I was wondering if you could comment on that, but also kind of going back to a discussion we had yesterday, I think, in terms of learning new things and what we can do to learn new things. Yes. And my argument there was, and I still stand by that you can do that by sort of letting these methods guide your intuition. And I was wondering if in this context and in the context of your talk that you could, I guess, comment on that in terms of learning new things.
So the sense in which I was using those two, and as I said, I'm not deep in ML, and so I may be using the words wrong. When I was talking about feature extraction or feature ID, I mean the morphology of clouds, the distribution of how their water might be arranged in space is unbounded, right? But there's only certain aspects of it that matter for the way the clouds interact in a 3D sense. So that's what I mean by feature extraction. That Tapia was saying we might choose to run our LES in certain regions based on what we need to learn most. I'm imagining that morphology is not, morphology writ large is not one of Tapia's targets, but it might be mine. And then the question would be, what aspect of that morphology do I need to get at? So that's the feature ID I want to do. The dimension reduction is actually a completely separate question, and I didn't talk about it at all, but it's roughly this business of how do we integrate over the spectra. So I don't mean to conflate those. I'm sorry if that's, if I did.
I mean, I guess that's the point of questions, right? But in terms of the morphology that you're talking about, I guess one of the things that I would see is that, I mean, you can look at the morphology just in the way it looks, right? But then you also have all the different angles and all the different interactions that you were mentioning. So in that sense, if you look at this naively, you can see this really complicated problem where you need to, model every cloud. But if you look at it in I guess in how I view feature extraction, in the sense that maybe there are groups of clouds and interactions that are more important than others that you might not necessarily realize intuitively when you're just sort of running all of these LES simulations, for example.
So I would be remiss if I didn't say it's not that we have no idea about what aspects of the clouds are important.
Yeah,
it's
sorry,
that our
efforts
to describe them with some parametric. I mean, that's what motivated something like Spartacus. But then when you find that Spartacus isn't working as well as you might hope, you're back to saying, well, maybe we need a somewhat richer description. And so it's that kind of thing, a little bit of guidance, a little bit more sharpening of my intuition that is the thing that I'm after in terms of the feature extraction. Yeah, maybe that's how I would describe it.
Yeah, I guess I'm sort of wondering about the search space you're using to some extent, but
we could. It's not that we know nothing about it. Maybe I won't rehearse it here, but I'd be happy to talk to you about it. But the ability to translate what our intuition about what we think is important into some low order parameters is not, as I showed you, not proved to work perfectly well.
Can we take a question from online now? So Duncan.
Yes, thanks. It's a nice talk, Rob. I was just curious. So I know NVIDIA have invested a lot of money in doing ray tracing online in games. And if this is something you've discussed with your NVIDIA contacts.
I have not been working on this problem. I have collaborators at Wageningen, actually Menno's graduate advisor, who's Giel van Geerwaarden, who they've done a little bit of this. I think it is really promising. So there's libraries that do this very, very fast on specialized hardware. I should look at you, I guess. There's libraries that do this fast on specialized hardware. I have not been able to figure out whether they are suitable for our problem, which doesn't only need the projection on a plane like they do in video games, but rather needs the full volumetric detail.
Right. Yeah, they probably take shortcuts, I guess. Yeah, okay, yeah, might be interesting. Thanks.
Tapio.
Thank you. I think the approach you outlined for using machine learning seems very appropriate for the tools and potentially very powerful. And I was curious about your wish list here. So you're building a new prioritization. It has outputs of mean fields, border variables, covariances, area fractions. Now, if you want to use the approaches you outlined, say, to correct for 3D effects that otherwise we don't have, is there a list of variables you wish you had access to that we don't provide?
So it's the spatial structure, right? So it's how those things are arranged in space is the single missing piece. The 2-point statistics are all
1D prioritization, right? I mean, something we can get out of a 1D prioritization that's predictive.
So I think the short answer is I wish I knew. I'm not sure it's possible, but I will chew on that and come back to you because this is the question. You know, yeah.
Any other questions? Yeah, one more. Dorit.
Follow-up question. And do you think it would be good enough to get the spatial structure correctly stochastically so that you would kind of be able to describe it from a spatial statistical point of view without actually knowing the exact details? I just wonder about these models. Huh?
So every time I look out the window, it sure looks quasi-stochastic. So I think the answer to that is yes. I think I don't know a way other than discrete realizations to do the radiative transfer problem, but I do not imagine that the general correction to the problem is deterministic in that way. Right. So that is to say, I think, yes, we could probably live with stochastic representations of cloud. We don't need to know everything. It's unclear to me, and this comes back to the dimension reduction question, exactly what we do need, and also to Tapio. It's not clear to me precisely what we do need to know. So one thing I didn't show you, for example, is that, or I didn't highlight, is that in Claire Singer's work, they have 2 sets of deep clouds, and one of them has aggregated in space and the other not. And so for those of you who are like following that whole literature, some of them are, oh, well, never mind, I've lost it. Anyway, if you go back to the slides, you'll see there's 2 deep convection cases, and they are the same, correct me if I'm wrong, except that one of them is in a big domain. And so the clouds all sort of clump together like good friends. And the other one, they are forced to remain scattered, and they have very different impacts on the radiative field. So, yeah.
Anish.
So the question is again on stochasticity and uncertainty. And I'm thinking of Sarah Jane Locke's work at ECMWF, where they have changed their stochastic parameterization to when you have clear sky radiation, then they remove the stochastic perturbations versus having stochasticity only in like not cloudy sky regions for radiation, right? So in this kind of a framework here, are you learning uncertainty, and when should it be stochastic versus deterministic?
Yeah, so it's a really interesting point. I think our understanding, the motivation for what Sarah Jane is doing is that our understanding of the clear skies is really, really good.
Exactly.
Right? And so there's nothing unusual about it. And the reason for introducing stochasticity when there are clouds is that there's a lot of the stuff that we have not resolved and do not know. And so therefore the calculation becomes substantially more uncertain. And the impacts of the 3-dimensional radiation flow are something we really don't know. So yes.
So would you say that there is one stochastic framework, or there's more uncertainty in certain regimes than even in the cloudy sky, like not clear sky? Yes, there is.
Yeah. So where clouds are more variable,
right,
and where there are more layers of them, this is where the uncertainty is greatest.
Right.
Not because you don't know how to do the radiative transfer, I really want to stress this, but because you do not know how the clouds are arranged.
Thanks.
Both Tapio and Robert want to continue the questioning at coffee, which you're free to go to after one more round of applause. We are reconvening at 4 o'clock, half an hour's time.